Welcome back to Dr. Liu's VCE Chemistry channel. Today, we are breaking down electrolysis and rechargeable cells from the 2025 NHT Chemistry exam. As I go through this, please feel free to correct any mistakes you find. All feedback from teachers, parents, and students is greatly appreciated. Secondary cells, or rechargeable batteries, are electrochemical cells where the chemical reactions are reversible. This allows the cell to be repeatedly discharged and recharged. During discharge, it acts as a galvanic cell, with the cathode as the positive terminal that accepts electrons. During recharge, it acts as an electrolytic cell, with the cathode connected to the negative terminal of the external power source, which supplies electrons. Aluminium metal is reduced from aluminium oxide via electrolysis. The reaction dictates that the production of 1 mole of aluminium requires the injection of 3 moles of electrons. Consequently, generating 2 moles of aluminium requires 6 moles of electrons, which corresponds to a total electric charge equal to 6 Faraday constants. If the current applied is 7A, the time needed for the process is calculated as the quotient of the required charge over the current, yielding. During the recharge of a silver-zinc cell, the zinc hydroxide at electrode Y undergoes reduction by gaining electrons. Consequently, electrode Y must be connected to the negative terminal of the external power source, as the negative terminal is the source that injects electrons into the circuit. It is essential to distinguish between polarity, the positive or negative terminal of the power source, and electrode identity, anode for oxidation, cathode for reduction, as electrode roles switch between charging and discharging. To derive the overall recharging reaction for electrode X, we must sum the two sequential oxidation equations. First, silver is oxidized to silver, 1 oxide, then, this intermediate reacts with hydroxide ions to form silver, 2 oxide. By combining these steps and cancelling the intermediate species, we obtain the net equation. To derive the complete equation for the silver-zinc cell during recharge, we follow a 3-step process. Determine the net reaction at electrode X. We sum the 2-stage oxidation of silver provided in the source. Silver reacts with hydroxide ions to form silver, 1 oxide, which is then further oxidized to silver, 2 oxide. Summing these steps and simplifying gives: identify the reaction at electrode Y. At the same time, zinc hydroxide at electrode Y undergoes reduction by gaining electrons to form zinc metal and hydroxide ions. Sum the equations. Finally, we combine the reactions from both electrodes and cancel the electrons and hydroxide ions that appear on both sides. Mark 1 silver oxides form because their half reaction E is lower on the electrochemical series than the plus 0.80 V required to produce Ag plus ions. Mark 2 the recharging voltage must be slightly greater than the sum of the electrode X potential and the 1.22 V potential from electrode Y. Mark 3 crucially, the high concentration of hydroxide ions ensures that silver reacts to form insoluble oxides instead of free ions, as long as the total voltage stays below 2.02 V, 0.80 plus 1.22. During discharge, the presence of hydroxide ions is just as critical as it was during recharge. They are consumed at the anode and produced at the cathode, acting as the shuttle that maintains the cell's internal alkaline environment. If the silver electrode were forming silver ions, the cathode potential would be plus 0.80 V. In that theoretical, but non-existent, case, the cell potential would be, however, since the actual cathode reaction involves silver oxides, which have a lower E than plus 0.8 eV, the E of cathode value is smaller. Yes, the standard cell potential is lower than 2.02 V during discharging. Because the silver oxide reactions occur at a lower potential than the plus 0.80 V required for Ag plus ions, the total push voltage provided by the cell during discharge will be less than the 2.02 V theoretical maximum. In practice, silver zinc cells usually discharge at approximately 1.5 V to 1.8 V, depending on whether they are using the AGO or Ag2O stage. In an artificial photosynthesis system, the flow of electrons is activated by light energy, specifically solar energy or photons. This light hits a photosensitizer or semiconductor, providing the kick needed to move electrons through the system. Since the goal is to produce hydrogen from water in acidic conditions, the reduction reaction involves hydrogen ions gaining electrons to form hydrogen gas. In both natural and artificial photosynthesis, water acts as the reductant, or electron donor. It undergoes oxidation to provide the electrons necessary for the rest of the cycle, releasing oxygen gas as a byproduct. Kim investigated the application of Faraday's laws using an electrolytic cell. Kim designed and performed the following method. Clean 2 copper strips with steel wool. Label one strip positive and the other negative. Record the initial mass of each strip. Add 200 ml of 1.0 m copper, 2, nitrate solution to a 250 ml beaker. Place the copper strips on opposite sides of 250 ml beaker so that the copper strips do not touch. Connect the positive terminal of a 6.0 V direct current power supply to the copper strip labeled positive, and the negative terminal of the power supply to the copper strip labeled negative. Turn on the power supply. Record the current in the circuit using an ammeter connected as shown in the diagram. Record observations about any changes occurring in the beaker. Turn off the power supply after 20.0 minutes. Detach the copper strips from the power supply, rinse with distilled water and allow to dry. Record the final mass of each copper strip. Repeat steps 1 to 12 twice. Calculate the average change in mass for each electrode. To improve the reliability of the results by minimizing the effect of random errors. Mark 1. CuCl2 contains chloride ions that can be oxidized at the anode to produce toxic chlorine gas, which poses a significant safety risk. Mark 2. The high 6V potential and the 2M concentration of chloride ions, non-standard conditions, make the oxidation of chloride ions more likely to occur than the oxidation of water. While the question specifically asks what variable Kim is controlling by using copper for both electrodes, your list correctly identifies the other factors that must remain constant throughout the 3 trials. Electrode material, using copper for both the anode and cathode ensures the same half-cell potentials and chemical environment. Electrolyte concentration, maintaining 1.0 m CuNO32 ensures the rate of reaction remains consistent across trials. Voltage. The power supply is fixed at 6.0 V to provide a constant driving force for the electrolysis. Time. Each trial is strictly timed for 20.0 minutes to ensure the total charge, Q equals IT, passed is comparable. To calculate the theoretical mass using Q equals IT, Kim must assume that the current remained constant at the value recorded in step 8 throughout the entire experiment. OR, the timing was exact, and the power supply was active for precisely 20.0 minutes without any delay in starting or stopping the stopwatch. Mark 1. identifying the physical loss of material at the negative electrode, cathode. Table 1 explicitly notes some particles observed below the electrode, meaning copper fell off. Mark 2, explaining that because this copper was lost to the bottom of the beaker, it was not included in the final weighing. This makes the result much less accurate for verifying Faraday's laws compared to the anode, where the mass change is more contained. To investigate Faraday's laws, Kim repeated the procedure, under the same conditions, using silver, Ag, electrodes with a solution of 200 ml of 1.00 m silver nitrate. Kim's hypothesis is that the amount of substance, mol, reacted at the positive electrode is directly proportional to the charge of the metal cation in the electrolyte. Kim's summary of results is presented in Table 2 below. Mark 1, the verdict: the results do not support Kim's hypothesis. Mark 2, data evidence: the data shows that the amount of silver is approximately 2 times the amount of copper. This contradicts the hypothesis because silver has a lower charge than copper, proving that moles reacted are not directly proportional to cation charge. The conclusion: for a constant amount of electrical charge, the amount of metal, in mole, produced is inversely proportional to the charge of the metal cation. Secondary cells, the essentials: reversibility. Secondary cells are rechargeable because their discharge products remain in contact with the electrodes in a state that allows the reaction to be reversed. Polarity shift. Discharge: galvanic anode is negative, cathode is positive. Recharge: electrolytic anode is positive, cathode is negative. Rule: the negative terminal of the charger always connects to the negative electrode of the cell. The silver-zinc cell, case study, recharge chemistry. During recharge, zinc oxide, hydroxide, is reduced back to zinc metal at the negative electrode. Voltage constraints. Ag+ ions are not formed because the high concentration of OH ions in the alkaline electrolyte forces the formation of insoluble silver oxides instead. The shuttle OH ions move through the electrolyte to maintain charge balance, consumed at one electrode and produced at the other. Faraday's laws and lab accuracy: the inverse relationship. For a constant charge, Q, the moles of metal produced, N, is inversely proportional to the charge of the metal ion. Example: Ag+, charge +1, produces 2 times the moles of Cu2+, charge +2. Experimental errors. Reliability: improved by repeating trials and averaging results to reduce random error. Accuracy: reduced at the cathode if the metal does not adhere to the electrode and falls off into the beaker. Artificial photosynthesis. The concept uses light energy to split water into hydrogen fuel. Key reaction: water acts as the reductant, source of electrons. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.